This PowerPoint presentation relates to the t-distribution and specifically to using the t-table. The objectives are: the student will be able to describe the properties of the t-distribution and find critical values associated with the t-distribution. The t-distribution, like the z-distribution, is a symmetric bell-shaped distribution. The mean of the t-distributions are 0. T-distributions are flatter and more variable than the z-distribution. That is, more probability lies in the tails and less in the center of the t-distribution than the z-distribution, especially when the degrees of freedom are small. As the degrees of freedom associated with the t-distribution increase, the t-distribution approaches the z-distribution. The exact shape of the t-distribution changes with the degrees of freedom. There is a different distribution of t for each possible number of degrees of freedom. This is different than the z-distribution or standard normal distribution. There is only one single normal distribution. However, there are a family of t-distributions. The shapes of all of these t-distributions are symmetric bell-shaped curves, and each distribution has a mean of 0. As the degrees of freedom get large, the t-distribution gets closer in shape to the standard normal distribution. This figure illustrates the relationship between the standard normal or z-distribution, the t-distribution with 20 degrees of freedom, and the t-distribution with 5 degrees of freedom. The solid line shows the t-distribution with 5 degrees of freedom. It is apparent that this is a symmetric bell-shaped curve that has its center at 0. There is a lot more distribution in the tails of this t-distribution with 5 degrees of freedom, again represented by the solid line, and less data in the middle, as opposed to the t-distribution with 20 degrees of freedom, which is represented by the distribution with the wide dashes. For the t-distribution with 20 degrees of freedom, you should note that there is a little bit less probability in the tail and more in the center, but still not to the extent that we see with the standard normal distribution. The normal distribution, represented by the small dashed lines on this figure, is the z-distribution, again centered at 0 with a standard deviation of 1. In looking at this figure, you should note again the t family of distributions do have a symmetric bell-shaped curve like the normal distribution. The center of the t-distribution is 0, like the normal distribution. However, t-distributions are flatter and more variable in the tails of the distribution than is the standard normal distribution. This is an example of an excerpt from the t-distribution. As you look at this table, you can see that the headings are called the proportion in one tail of the t-distribution, and also a label for the proportion in two tails combined of the t-distribution. Focusing specifically on the proportion in one tail, that is denoted by 0.05, and following that column down, the column that has 5% in one tail refers to the same column that has 10% in two tails. Recall that the t-distribution is symmetric. If there is 5% in one tail, there is 5% in the other tail. For the t-distribution with 1 degree of freedom, that is, following the first row of the t-distribution across, you can see that the t-score that has 5% in the tail for 1 degree of freedom is 6.314. That is, there is 5% of the data to the right of the positive value 6.314 and also 5% of the data to the left of the negative value 6.314. Note that there are no negative values represented in the t-distribution because the distribution is symmetric. Once again focusing on the t with 1 degree of freedom, the critical value of 6.314 has 5% of the data above it. The critical value of negative 6.314 has 5% of the data below it. Thus, that same column labeled proportion in one tail 0.05 refers to the same distribution that has proportion in two tails combined of 10%, 5% on each tail. This is an example of finding a critical value for the t-distribution where the degrees of freedom are 3. We are looking for a two-tailed test and the alpha value is set at 0.10. The first thing to do is locate the degree of freedom 3 row. This is the row of the t-table that the critical value will come from. The next piece of information to note is that we are dealing with a two-tailed test. Therefore, we want to look in the proportion in the two tails combined column. The alpha value that is chosen in this problem is 0.10. So we want to look down the alpha equals 0.10 and across the degree of freedom row to see that the critical values for this two-tailed t-test would be plus and minus 2.353. That is, the score of negative 2.353 has 5% of the data to the left of it. The score of positive 2.353 has 5% of the data to the right of it. Therefore, the t-critical values for the t-distribution with 3 degrees of freedom, looking at a two-tailed test at alpha equal 0.01 are plus and minus 2.353. As another example, if you're asked to find the critical values for the t-distribution for degrees of freedom equals 6, a right-tailed test carried out at alpha equals 0.05. The degrees of freedom of 6 tell you that you'll follow that degree of freedom column down to row 6. The fact that we have a right-tailed test indicates that we will find the proportion in one tail, specifically the right tail. We are working at alpha equals 0.05, so we'll want to follow the proportion in one tail 0.05 column down to the intersection with 6 degrees of freedom to find our critical value of positive 1.943. That is, the t with 6 degrees of freedom with 5% of the data above it is 1.943. As another example, if you find the critical values for the t-distribution with 4 degrees of freedom, carrying out a left-tailed test at alpha equals 0.01. Again, the degrees of freedom tell you the row of the table that you'll be looking in. We are conducting a left-tailed test at alpha equals 0.01, so we want the proportion in one tail column of 0.01. We want to follow that down to the intersection where the degrees of freedom equals 4 to the critical value of negative 3.747. The critical value is negative because this question asked for the critical value for a left-tailed test, meaning that the rejection region is in the left tail or the negative end of the t-distribution. Recall that t, like the z-distribution, is centered at 0, so negative scores indicate values below the mean. To find the critical value for a 90% confidence interval based on n equals 7 observations, the degrees of freedom are 6, so we will look in the row 6 of the table. We are looking for a two-tailed test at alpha equals 0.10. If we have a 90% confidence interval, the alpha is the proportion of data that is left over, 100 minus 90% or 10%, or alpha equals 0.1. If we look at the two-tailed column for 0.1 for the intersection with degrees of freedom 6, we see that the critical values are plus and minus 1.943. If we were asked to find the first percentile of the t-distribution with 4 degrees of freedom, recall that a percentile tells us how much of the data is at or below that score. We are looking for the t-score that's at the first percentile, or the t that has 1% of the data below it. Thus, we will be looking in the proportion in one tail 0.01 column. We go down to the degrees of freedom equals 4 row and find the critical value is negative 3.747. The reason that the critical value is negative is because we are looking for the first percentile, the score that has 1% of the data at or below it. This, of course, in the t-distribution will be a negative value. As another example, if we find the t value with 4 degrees of freedom that separates the top 10% of the distribution. In this case, we need the one-tail proportion of 0.10. We are trying to separate the top 10% of the distribution from the remainder. The t, we are told, has 4 degrees of freedom, so we will look in the 4 row and the one-tail alpha of 0.1 column to find the t critical value of 1.533. This t value is positive because we are looking for the score that separates the top 10% of the data out. When looking at the t table for critical values, the degrees of freedom that you need may not be in the t table. If the degrees of freedom are not listed, you should use the row below the degrees of freedom that are listed. That is, if you need the t with 42 degrees of freedom and you look in the t table and the row of 42 is not present, you should use the t for 40 degrees of freedom. If the sample size is very large, however, you should use the final row of the t table, the row that is labeled infinity. Note that the critical values in this row should look familiar to you because these are the z critical values. That is, the critical values in the last row of the t table are the z critical values. This is why the t-test and z-test are very similar, and we say that the z can replace t for very large sample sizes. As the sample size increases, the t-distribution starts to look exactly like the z-distribution, and then the critical values become one and the same for the two distributions. Again, the objectives for this presentation were to be able to describe the properties of the t-distribution. Recall that the t is a family of distributions with a mean of 0. They are symmetric bell-shaped curves, and there is one t-distribution for every degree of freedom. Generally, the t-distributions have more probability in the tails and less in the center than the z-tables. The next objective is to find critical values associated with the t-distribution.